Okay, let's skip the fluff and start with a hard truth. You are probably throwing away entire mark bands on your Cambridge Physics 0625 exam right now without even realizing it. We are not doing a standard, boring review today, no way. Instead, we're reverse engineering a full mark examiner-approved answer for free fall and terminal velocity. That's right, we're going to start from the perfect final answer and work entirely backwards to uncover exactly how to secure those top marks. So let's look at a prime example of where things go terribly, terribly wrong for most learners. Take a look at this painful learner mistake on the left. A student looks at a curved graph right at the start of a fall and writes, "The parachutist is slowing down at A." That right there, that's a zero-mark trap, and it absolutely destroys grades. Why? Because they're completely confusing the visual shape of the curve with the actual physical value it represents. Now check out the right side. Speed increases, she accelerates. Boom, full marks. It's concise, it uses the exact correct terminology, and it connects directly to the physical reality of the parachutist. This whole explainer is about getting you to use that perfect examiner-approved wording. So why does ordinary revision just fail? You know how it goes. You read the textbook, you memorize the formulas, but you walk out of the exam and you've still lost marks. Well, the data coach for Cambridge 0625 highlights exactly why standard studying falls short. It's these incredibly common exam pitfalls: missing units in the final step, rounding off way too early, giving vague explanations, literally misreading the axes entirely, suggesting weak practical improvements, picking the wrong variables, or, my personal favorite, writing conclusions that aren't even supported by the data. We have to completely shift your mindset. All right, here's the game plan to fix those mistakes: the mark scheme framework. To stop thinking like a stressed student and start thinking exactly like a Cambridge examiner, you need to follow these 4 steps every single time you look at a data question. Step 1, identify the core concept. Are we dealing with acceleration or terminal velocity? Once you've nailed that, step 2 is finding the evidence or data. What is the graph actually showing you? Then, step 3, apply scientific reasoning. How does that specific data prove the concept? And finally, step 4, the most crucial one, examiner wording. Translate your reasoning into the exact vocabulary the mark scheme demands. Now listen closely, because in just a moment, I'm going to share a massive secret with you. I'll show you the exact physical context clue that literally transforms a zero-mark calculation into a full-mark answer. It is a very specific trap that examiners love to set on curved graphs. And honestly, if you don't know this clue, your calculation will be completely wrong, even if your math skills are perfect. You absolutely cannot afford to miss this if you want those method marks. But first, we need to build the foundational framework that makes that clue super obvious. Okay, let's build that foundation. We've got a speed-time graph here of a parachutist falling from a hot air balloon. Physicists use graphs exactly like this one to take complex, chaotic, real-life events and translate them into pure, understandable data. By tracking the changing shape of this curve and explaining what's happening to the gradient and the dependent variable, which is the speed over there on the y-axis, as time ticks by on the x-axis, we can perfectly map out the parachutist's entire journey. And this table right here, this is basically your exam cheat code for extracting that data. You have to know your graph rules cold. On a distance time graph, the gradient is simply the speed. But notice the massive difference in the second row? This is where the magic happens for speed time graphs. The gradient is equal to the acceleration. A downward sloping line means they're decelerating or slowing down. A perfectly horizontal line means no change in speed. They are moving at a constant speed. And crucially, the area under the graph equals the total distance traveled. Memorize this matrix. Let's put our 4-step framework to the test. Look at point A. The parachute has just started to fall. Using our examiner wording, her speed increases, therefore she accelerates. Simple, right? Now, as we move to point B, notice the curve. The speed is still increasing, so yes, she is still accelerating, but the gradient is getting less steep. Therefore, the acceleration is actually lower. Finally, we hit point C. The curve completely flattens out. The speed has reached its maximum value and stays exactly the same. Which brings us to a vital Cambridge definition that you must know verbatim. Terminal velocity. A constant speed reached when acceleration is 0. Look closely at the graph. This happens exactly between points C and D. The line is perfectly horizontal, meaning the speed is constant and the acceleration is mathematically 0. But, and this is super cool, as we'll see further along in her fall at point F, she actually reaches a new, lower constant speed. This is a second terminal velocity, and once again, the acceleration is 0. Okay, now keep your eyes glued to point D. After falling at a constant speed, the parachutist yanks her parachute open at exactly 28 seconds. Look at the immediate, drastic plunge in the graph. The speed decreases incredibly rapidly. Because the gradient is extremely steep and pointing downward, this represents a very high deceleration. This real-world physical event completely flips the math we apply to the graph. All right, challenge time. I want you to actually pause this explainer right now. Seriously, grab a piece of paper. Based on the graph we just looked at, I want you to apply our framework to find exactly where the graph line changes most dramatically, and then calculate the acceleration when the change in speed was greatest. Think about the physical context we just broke down. Where is that gradient the absolute steepest? Pause it now, write down your answer, and let's see if you can beat the examiner trap. Okay, let's see how you did. Here is the examiner-style correction. If you just grabbed two random points on the axes to do a slope calculation without thinking about what the parachutist was actually doing, oh man, you fell for the classic trap. You might have forgotten your units or accidentally calculated an average over the whole fall. To get full marks, like the answer on the right, you must let the physical context guide your math. You had to identify that the steepest gradient, the highest deceleration, happened right when the parachute opened after point D. You secure those method marks by proving to the examiner you actually understand the physics behind the numbers. Remember that open loop from earlier? Well, here is your ultimate examiner clue. A negative relationship is a downward sloping line. It's that simple, but so many miss it. As the values on the x-axis increase, the values on the y-axis fall. On our speed time graph, this happens right from D to E to F, and again from G onwards as she hits the ground. Recognizing this negative relationship immediately proves deceleration. If you miss this clue, you'll probably calculate a positive number, and you will lose all the marks for that question, because your math doesn't reflect the physical reality of her slowing down. So what is the big takeaway here? It's this golden rule. Whenever you are faced with a data analysis question in physics, you must always ask yourself, when a graph line changes, what new physical description or calculation is needed? You can't just read numbers blindly off a grid like a robot. Everything depends on the physical context. Connect the gradient, whether it's getting steeper, going flat, or plunging downwards, back to the real-life physics happening to the object. Flat line, terminal velocity. Sharp drop, high deceleration. Always connect the math to the motion. So we've successfully reverse-engineered the physics and the math, but there is still one massive piece of the puzzle missing. Think about it. Even if your calculation is flawlessly executed, if you don't answer the specific command word the examiner uses, like the difference between describe and explain, you are still going to lose marks. Are you really ready to let bad vocabulary dictate your grade? To master the exact command words that decide your final mark band, you absolutely need to watch our next explainer. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. See you in the next one.